Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. Question for you. Okay? First off, how many days, if the Earth starts at this location in its orbit, okay, right there, how many days must pass in order for it to return to the same position? You got it? Yeah, good. And I'm gonna guess that some of you said 365, right? 365. What we know is that we define a year based on how long it takes for the Earth to return back to the same position. If we wanted to be 100% accurate, we would have to say this. It takes 365.242190 days to return back to the same position. Okay? And notice, very important here, is that we have this leftover decimal place. Okay? That's the key. Okay? You got that in mind? Good. Okay. So the next question, okay, and this is why I left it purposely ambiguous. I expected some of you to say 365, others to say 366. Maybe some of you said 365.25, which is quite a bit closer. Okay. Yeah, good. So next question. Okay. The figure below shows the location of the Earth. Okay. Where will the Earth be located exactly 365 days later? Okay? And this is why I've colored the background. You can say, okay, it'll be in the blank color background, or maybe it's a solid or a dash. Go ahead. Yeah, you got it? Yeah, good. Because it takes 365.24 days to get back to the same position. If we lop off that decimal point and we just do 365, that means that the Earth doesn't have quite enough time to get back to the same location, right? And so what happens? Well, the Earth is going to be just shy. I'll draw it in right here just for illustrative purposes. It's going to be a little bit short of the previous position. Right? We just haven't given it enough time. Now what happens? Well, that's after year 1. And then we go to year 2. We're still a little bit short. We go to year 3. And after the 4th year, so 2, I'll just label this 2, 3, and 4. After that 4th year, we're how far behind in our orbit? How much time do we have to give the Earth to catch back up? Yeah, go ahead, calculate it out. Yeah, you got it? Yeah, good. We're going to take this extra decimal, right? We've ignored this excess for 4 consecutive years. Okay? So what we'll do is take that excess, we multiply by 4, and we see that we get almost rounded approximately an extra day. So on that 4th year, right, the Earth is short, it's short. On that 4th year, we insert an extra day into our calendar system, right? And that gives the Earth the extra time that it needs in order to get roughly back at its same position. Right? It's like every year we short the Earth just a little bit of time. And so every 4th year we say, okay, we'll give you the extra day to get back to the right spot. That's cool, right? Okay, good. So next question for you. Okay? So after 4 years, including the leap year, okay, is the Earth ahead or behind in its orbit? So we've inserted that extra day. Yeah, and here I'll just have it graphically, right? After the 1st year, we're behind by about a little under 6 hours, and then a little under 6 hours again and again. But when we add in that leap day, Notice, if I add all 4 of those together, I get some value that's less than 1, right? I said, oh, we're going to go ahead and round. We'll round up to a full day. But in reality, it's 0.96 days. So when we add in that leap year, right, we add in that extra day, give it a little extra push or a little extra time to catch up, we are now slightly ahead in our orbit, right? 3/100ths of a day too far in the orbit. Okay? So at the end of a 4-year group, including the leap year, we see that we've given the Earth a little too much time, right? It's a little too far ahead in its orbit by about 3/100ths of a day. Okay? So next question, how many days ahead in the orbit is the Earth if we've done 100 leap years? Yeah, you say, oh, I got this, Greg. For every leap year, we're ahead by 3/100ths. So after 100 leap years, right, we just move the decimal point over 2. Yes, indeed. Okay? And 100 leap years, that corresponds to 400 years. Yeah, so after 400 years, including leap years, the Earth is too far ahead in its orbit by about 3 days. Okay? And that creates some really interesting problems. Yeah. So, and to highlight that problem, I'll ask you 2 questions. First of all, how do we determine the first day of spring? Yeah, you got it? You got an idea? Well, remember, if we sit out and we watch the sun over a course of a year, we'll notice that some days in the year, if this is the horizon, there are some days of the year where the maximum altitude is really low. And then as the year progresses, we'll get a higher and higher altitude of the sun until it hits the peak, right? And there, it's the highest above the equatorial plane. It's directly above the Tropic of Cancer, and that is known as the summer solstice. Similarly, at its lowest altitude during the year, it's above the Tropic of Capricorn, it's below the equatorial plane, and it's the first day of winter, the winter solstice. Okay. Well, how about halfway between, when it's directly on the equatorial plane? Yeah, we call those the equinoxes. And that defines our first day of summer. The first day of spring. That moment when it crosses the equatorial plane depends essentially on where the Earth is located in its orbit. Okay? I'll say that again. The sun crossing the equatorial plane is dependent, the date that occurs depends on where the Earth is in its orbit. Okay? So, if I'm thinking about this problem, okay, for every 400, we'll say 4 years. Okay? 4 years, the Earth is too far ahead in its orbit. Okay? So the question then becomes, will the first day of spring be earlier or later in the calendar year? Will the Earth arrive back to the correct position in space too early, according to our calendar, or too late? Yeah, good. If the Earth is ahead in its orbit, that means that the Earth is going to, the first day of spring is going to occur earlier in the calendar. So let's say, just to give you kind of numbers, let's say the first day of spring in the year 0 occurs on March 21st. That means in year 400, for example, the Earth is 3 days too far ahead in its orbit, and now the first day of spring occurs on March 18th. Well, we go another 400 years, and now the first day of spring occurs on March 15th. And you kind of see what's going on, right? I mean, by the year 1600, the sun is crossing the equatorial plane on roughly March, 3 days. So we're talking March 9th. That's weird, right? The year 1600, excuse me. Okay. And it's because we add in that little 300ths of a day excess every leap year. We wouldn't notice that for during the course of a single person's lifetime, but over the course of several millennia, that effect really starts adding up. Okay? Yeah. So this is kind of the basis for, well, no, I shouldn't say kind of. This is the basis for our leap year system. Okay? So timekeeping. The idea that we have leap years every 4 years comes to us from Julius Caesar. And I believe it was instituted somewhere around 52 BCE. Okay? So every 4 years have a leap year. That idea was initiated in 52 BCE. Now we're going to do just a wee bit of history. Okay? Part of it would be, why do we care about when the first day of spring is? Why is it kind of problematic to have it moving in our calendar system? In one sense, it's not. We could just deal with it and that would be okay. But here's an important historical event, the Council of Nicaea. The Council of Nicaea was a congregation of the Roman Church, and what they determined in the Council of Nicaea was they set the day on which Easter would occur. The Council of Nicaea was 325, and one of the things they did was they said, okay, we are going to set Easter according to this rule. We are going to wait for the first day of spring. So we have to wait for the spring equinox. Then we are going to wait for the first full moon. So the first full moon after the spring equinox. And the Sunday after that is Easter. Okay? So you got that process. Number one, we need the spring equinox. Okay? Then we wait for the first full moon. Okay? And then after that, the Sunday is Easter. Okay, you got it? So here's the problem. Okay? If the Earth is arriving earlier and earlier according to the calendar, right? The spring equinox is arriving earlier in the calendar system. That means that Easter is progressively earlier and earlier in the calendar year. Because we didn't define it as a specified date, we defined it relative to the first day of spring. Okay? And so what's the problem then? Well, the church did not like the fact that Easter was getting progressively earlier and earlier in the year. And they said, this has got to stop. We have got to take care of this 3-day excess that happens every 400 years. So in almost a millennium and a half later, so I have this as 1582. Okay? The Roman Empire introduced the Gregorian calendar system. They said, that idea about leap years every 4 years, let's keep that. But because we have this 3-day excess every 400 years, we are going to introduce another rule. That rule will be, we will exclude a leap day in years divisible by 100. So if it's divisible by 4, you have a leap year, unless it's also divisible by 100, and then you don't have a leap year. Okay? And then it turns out if you're divisible by 400, then you do have a leap year. Okay? Now, the other problem, because this was introduced almost 1600 years later, right? That corresponds to, roughly speaking, you're about 12 days too far in your orbit. Okay? We've got to get rid of that somehow. Rather than the spring equinox occurring on March 9th, we want it to occur on March 21st. So what happens? In the Roman Empire, in the year 1582, they shifted the calendar. They basically said, okay, today is March 10th, tomorrow will be March 21st. We have to get our calendar to rematch the position of the Earth in space. And so in the Roman Empire, 1582, the calendar jumped over those 11 days to realign the calendar with where the Earth is positioned in space. And since then, this Gregorian calendar system, that is sufficient to make sure that the first day of the spring equinox, the first day of spring, occurs somewhere between March 20th and March 22nd. And this correction will also build up some errors, but I think you have to go something like 40,000 years into the future to get an extra day. So this will be pretty good for quite some time. Okay? Of course, I always find this another interesting history bit. Okay? In 1582, that's the Roman Empire, and primarily under the guidance of the Pope. Okay? The Catholic Church, in other words. But there's this other empire who is separate from the Catholic Church. Okay? And in fact, I believe how it goes is the leader of this other empire wanted to divorce his wife. The problem was his wife just could not produce a male heir. Of course, now we know that it was actually a king's fault, but that's, okay, what are you going to do? So what happened? Well, the king goes to the Pope and says, I would like you to grant me a divorce. And here's the problem. The king is actually married to, I believe, the Pope's niece or cousin. Can't remember if it's niece or a cousin. You think the Pope's going to let you divorce his family member? No, absolutely not. So this leader, I believe it was Henry VIII, double check here, I believe it was Henry VIII, said, fine, you will not allow me to divorce my wife. I do no longer recognize you as the authoritative figure of the church. I am going to go back to England and I am going to start a new denomination. Or maybe it's a new sect. Okay? And I am going to be the head of that church. Right? Not the Pope, but rather the King of England is going to be the leader of the Church of England. And as leader of the Church of England, I hereby approve the divorce from my wife. So I go into this little bit to highlight that the British colonial empire does not recognize the Catholic Church as the authoritative figure. It wasn't until the Calendar Act of 1750, that the British Empire recognized that they needed to adjust their calendars. And so in the British Empire, they did not convert to this Gregorian calendar system until 1752. At that point, they had extra days in their calendar system. And so instead of skipping 11 days, they had to skip 12. So I've gone, and this is just from timeanddate.com, okay? But you see that, it looks really funny. The month of September only has 20 days in it. Yeah, so you got to be careful, right? We're part of the British Empire. You will not find any documentations on this. Like, right? Like you just skip over it completely. Okay. I always wonder, does that mean I get a full month's wages? But then do I also have to pay a full month's rent? I mean, can you imagine the logistical nightmare for this? Yeah. Okay, good. So that's kind of, that's the origins of the leap year. Is it has nothing to do about extra days, or I mean, it has everything to do with making sure that how we keep track of days corresponds with the Earth's position in space. Pretty cool, right? Yeah, okay. So for sake of completeness, I kind of like this calendar thing. I thought, well, I should probably mention some other ways of doing a calendar system. The calendar that you all know and love, I imagine, is what's called a solar calendar. Okay? It uses the position of the sun to determine the length of a year. Okay? But you don't have to do that. You could find other calendar systems. So for example, there's one called the lunar calendar system. And how the lunar calendar system works is that your months are based on the time it takes for the moon to complete an orbit of the Earth, roughly 29.5 days. Okay? So you have 12 months of 29.5 days. Of course, you don't do it that way. You do 29 the first month and 30 the next month. And you go back and forth, 29, 30. Okay? And after 12 lunar months, you say, okay, that is a lunar year. Okay? Now, of course, we could always do the math, but if you do something like 29 times 6 and 30 times 6, okay, what do we get at the end of the day? Well, we get 180 times 2, so that's 360, minus 6 days. So this is 354 days. Okay. You know that, okay, so a lunar calendar only has about 354 days. Okay. So why is that important? Well, let's go here. It's the Islamic calendar. Okay, is a true lunar calendar. The Islamic calendar still preserves the use of the lunar calendar for religious holidays, religious festivals. Okay? So if we actually compare the date of a religious festival in the Islamic faith, okay, and we compare it to the date in the lunar calendar, we see that the date on the solar calendar always changes. Okay? So for example, if we're dealing with Ramadan, Ramadan is the 9th month of the lunar calendar. Okay? If you're not familiar, Muslims will fast from sun up to sundown in celebration of Ramadan. And then once the sun has set, then there's generally a large celebration where you break your fast for the day. Okay. And then the next morning, the same thing. Generally, you even have to abstain from drink as well. Okay. So usually it's not even any liquids. Okay. So this is the date at which the Ramadan occurs. This is the year in which Ramadan occurs. So it's the 9th month of the year 1435. Okay. That's the lunar calendar. Well, you notice in the solar calendar, that corresponds to June 28th. But the following year, the next year, okay, in the lunar calendar, 1436, and you notice it's not again on June 28th, right? It's almost 10 days earlier. Why? Why is it shifting? Well, don't forget, a lunar calendar is about 10 days, I'll estimate, 10 days shorter than the solar calendar. That means that Ramadan, if you're keeping track of Ramadan on a solar calendar, it's going to shift and be 10 to 11 days earlier every year, right? There are other calendar systems that are based on either cultural or religious holidays. You also have some that are called lunar solar. Okay. So, for example, the Chinese calendar, the Chinese New Year calendar is a lunar solar calendar. Okay. Or, for example, Hebrew, Hindu, and Buddhist calendars. The Hebrew calendar is interesting because it is lunar, but what they do is every once in a while, rather than inserting a single day to correct their calendar system with the position of the Earth in space, they insert an entire month. So they get a leap, for lack of a better word, I'll say a leap month, where they make up that lost time, okay, or lost time. They give the Earth an extra 30 days or so to catch back up in its position. Okay? Again, those are all for either cultural or religious events. They still, if you go anywhere, everybody's going to still use the solar calendar for doing business dealings in everyday life. Okay, sweet. Well, I think that is by far enough. I'll have a review question starting at the next lecture just to kind of get our brains rolling again. I thank you for your attention. Keep up the good work. I'll see you next time.